Let's work on some more exponential functions. I think this is 6.3 still. And we're going to talk about transformations that we can apply to exponential functions. So these are going to be the same transformations that we've applied to all of our parent functions in the past. So remember that the basic parent function for this family is y equals a to the x. So this is our parent function. And then any other thing that appears in the equation is going to be a transformation. So if we have a number that is multiplied out front, so it's not in with the base, it's multiplied separately out in front of the base, that is going to be a vertical stretch or compression. Remember that stretches are when the number out in front is bigger than 1, and compressions are when that number is between 0 and 1. If that number is negative, then that is going to be a reflection over the x-axis. So that turns your graph upside down. And the way that we are going to handle that in terms of what we do to our 3 special points is that we will multiply our y values by that number. Okay, other transformations. If there is a number added or subtracted up in the exponent with the variable, that is going to be a shift left or right. It is going to be left if it's positive. It is going to be right if it's negative. And what we're going to do is we are either going to subtract that number from the x's or add that number to the x's, depending on if we're shifting left or right. If we have a number multiplied in the exponent with the x, these are horizontal stretches and compressions. So this is a horizontal stretch if that number is between 0 and 1, or compression if that number is bigger than 1. And if that number is negative, we are going to reflect over the y-axis. What we're going to do with this number to our ordered pairs is we are going to multiply our x values by 1 over the number. The next transformation we're going to look at is the shifting up or down. And that's if we have a number added or subtracted down on the same level as the base. And that is a shift up if it is added, or down if it is subtracted. So what we do with that is we add that number to our y values if it is a shift up. We subtract that number from our y values if it is a shift down. Alrighty, we're going to still follow the order of operations when we apply these transformations. So, for example, if I am multiplying my x values and adding and subtracting my x values, I'll do the multiplying first, then the adding and subtracting. Same thing here. I would apply stretches and compressions first, and then shifts second. All right, here is an example. So if we have y equals 5 plus 3 raised to the power of x minus 2, that's the same thing as y equals 3 to the x minus 2 plus 5. So you may see it in this order, but because of the commutative property of addition, it means the same thing as this. So this plus 5 that's out in front is the same as a plus 5 at the end, which is going to make that a shift up. So kind of first off, you want to identify what is the parent. And the parent is going to be the y equals the base of 3 to the power of x. Everything else is a transformation. So you always do want to know that your parent is going to be y equals 3 to the x. That's going to allow you to identify your 3 starting points and your horizontal asymptote. So our 3 starting points would be -1, 1 over base, so 1/3, 0, 1, and then 1 base, which would be 1, 3. And then our horizontal asymptote on exponential functions will be y equals 0. The transformations that we have, this guy up here, -2, that is a shift right 2. Oh, I made that the wrong color, you guys. That should be pink. That's my bad. You probably already caught that. Shift right 2, because I like to match it with my notes up there. So shifting right 2 means that I'm going to add that number to my x's. So I'm going to take all of my x coordinates and I'm going to add 2 to the x's. So I'm going to take all my x's and then I'm going to add 2. Then the other transformation that I have in here is the plus 5. And that is going to shift, because it's added, it's going to shift up. So when we shift up 5, that means we are adding that to our y's. So we're going to take all of our x's and add 2. We're going to take all of our y's and add 5. And that's going to give us our new coordinates for that transformed function. So -1 plus 2 will be 1. 1/3 plus 5. 5 would be 15/3. So plus 1/3 would be 16/3. And then 0 plus 2, 2. 1 plus 5, 6. 1 plus 2, 3. 3 plus 5, 8. Now the horizontal asymptote is also going to have a transformation. Since it is a y, we also add 5 to the 0 there. So we have y equals 5. So when we go to graph this, 1, 2, 3, 4, 5, we put our horizontal asymptote at y equals 5. And then we graph our 3 ordered pairs. So 1, and then 16/3, remember, was 1/3 plus 5. So 5 1/3. 2, 6, and 3, 8. Oops, I put that at 7. 3, 8 will be here. We remember when we graph these that we need to go through all 3 of these points. One end of the function is going to go along the asymptote. The other end is going to zoom away from the asymptote. So here we go through these 3 points. This end is going to zoom along the asymptote. This end is going to zoom away from the asymptote. So that's what our graph will look like. The domain, of course, for all exponential functions is -infinity to infinity. And then the range is related to the horizontal asymptote. So it's going to, this function starts at 5 and goes towards infinity, but never equals 5. So it will be 5 to infinity with a parenthesis. Okay, let's see what we got next. Y equals 5 to the 3x plus 2. Okay, again, figure out what is your parent. Y equals 5 to the x. That's going to allow us to get our 3 original points. So our function originally would be at -1, 1/5, 0, 1, and 1, 5 with a horizontal asymptote at y equals 0. Now let's talk transformations. The +2 at the end, right here, is a shift up 2. So that means that we will add 2 to the y's. And then the number that is out in front of the x there, since it's up in the exponent with the variable, that means it's going to be a horizontal stretch or compression. That number is bigger than 1, which means it's going to be a horizontal compression. Horizontal compression. So what that tells us to do is to take all of our x's and multiply them by 1/3. So we're going to take all of our x's and we're going to either divide them by 3 or multiply them by 1/3. And then we're going to take all of our y's and add 2, which will do the shift up 2. So we've got -1 times 1/3 is going to give us -1/3. And then 1/5 plus 2, well, 2/1 would be 10/5. So 11/5. 1/3 times 0, 0. 2 plus 1, 3. 1/3 times 1, 1/3. 5 plus 2, 7. And then the horizontal asymptote, also a y value, so we add 2 to get y equals 2. My graph's not here. Two, 3, 4, 5, 6, 7. We don't need very many on the x-axis because we're only going from -1/3 to 1/3. So we got -1/3 and then 2 and 1/5. 1, 2, and 1/5. 0, 3, and then 1/3, 7. We have a horizontal asymptote at y equals 2. And then when we connect our 3 points, we're remembering that one end zooms along the asymptote, then we go through our 3 points, and the other end zooms away. It should not turn back towards the axis. It should continue to grow out, but very slightly in this case. Let's look at our domain and range. Domain for all exponential functions, -infinity to infinity. And the range on this one starts at 2, goes to infinity, but does not include 2. So it will be 2 to infinity with a parenthesis. All right, now we have a function that has e in it. So a natural exponential function. So here's where we're going to talk about when the base is between 0 and 1, because 1/e, remember, is pretty close to 1/3. So another way to think of 1/e is to think of it like e to the -1, because remember that those negative exponents are going to switch the base from the numerator to denominator or vice versa. So e to the -1 would become 1/e, and that allows us to write 1/e as e to the -1. And then by the properties of exponents, when I raise a power to a power, e to the -1 raised to the x, I multiply those exponents. So that becomes e to the -x. So now I have y equals -5e to the -x. And that's going to be the function that we graph. is the same as this function here. So remember, the first thing we want to do is identify the parent, and that is going to be y equals, the base is e, the exponent is x. So y equals e to the x is the parent. And that's going to give us our 3 starting points. So remember, the starting points are -1, 1 over base. The base is e, so -1, 1 over e. And then 0, 1, and 1 base, so 1e. We still have a horizontal asymptote at y equals 0. Then we're going to apply some transformations here. The transformations we have, this time we have a number out in front. We have a -5. Well, this is actually 2 transformations, but we're going to handle them in one step. So this negative means we reflect over the x-axis, and the 5 means we have a vertical stretch of 5. When we put those together, that just means we're going to take all of our y's and multiply them by -5. The other transformation we have is number multiplied by the x. This is a -1. So a 1 would be not a stretch or a compression. That will be the same magnitude, like it's not going to stretch it or compress it. But that negative means we're going to reflect over the y-axis. And so what we're going to do is take all of our x's, and technically we're going to multiply them by 1 over -1, but that's the same thing as taking all of our x's times -1. So our transformations are going to require us to take all of our x values and multiply them by -1, and take all of our y values and multiply them by -5. All right. So we'll take our -1 times -1 will be 1. And then 1 over e times -5 would be like -5 over e. But if you remember thinking that 1 over e is about a third, when we go to graph this, we can just roughly eyeball it as -5 thirds. Or alternatively, you can get your calculator and do 5 divided by e, so -1.8. So a little off from -5 thirds, which would be -1.7, but close enough when we're going to graph them. Definitely not close enough if my math lab asks for a decimal approximation. You should use your calculator. But for eyeballing on a graph that you're drawing by hand, -5 thirds is going to be close enough. I will know where you're headed because you will also have this ordered pair on your paper. Okay, next one. 0 times -1 stays 0. 1 times -5 becomes -5. 1 times -1 becomes -1. E times -5 becomes -5e. This one you're going to want to, -15 is not close enough. So we would want to do -5 times e to get a decimal approximation about -13.6. If you're working with a calculator that's not a graphing calculator, it's going to be close enough if you do 5 times 2.7. If you graph 13.5, that's going to be fine because, of course, when we take a test that has graphing on it, you won't use a graphing calculator, but you will be able to use a regular calculator. And as long as you know that E is about 2.7, you can get that figured out. Same with the dividing, if you did 5 divided by 2.7. Now our horizontal asymptote is a y value, so we also take 0 times -5, which leaves us at y equals 0. So let's get those graphed on there. I'm going to start with my horizontal asymptote at y equals 0, and then my ordered pairs. So 1, negative 1.8, 0, negative 5, and negative 1, negative 13.6. 2, 4, 6, 8, 10, 12, 13.6. When you go to graph this, remember your guidelines that you're going to go through all three ordered pairs. One end is going to zoom along the asymptote, the other end zooms away. So as I think about connecting these, this is zooming me away from the asymptote, which means this end will need to zoom me along the asymptote. Domain for this function, as all exponential functions, negative infinity to infinity. And the range, remember, is always related to the asymptote on these functions. But this one goes from negative infinity up to 0, but does not include 0. So this range will be negative infinity to 0 with a parenthesis. Next section is one-to-one property of exponents. So we'll come back and do that in another video.